So let's start with the end in mind. So here is an experimental and very much research-oriented interface for exploring understanding natural language with ontology. So what I have here is our simple default query of Robert kicks the cart, and I'll walk through the steps of processing that are shown here in the SigmaNLP system. We start out by having the Stanford Core NLP system do some tagging, parsing it and determining parts of speech. So Robert is a proper noun, an NNP, and we map the proper name Robert through a proper name dictionary that we have that's not originally part of Stanford Core NLP. And we map it to the SUMO notion of man, a male human. And we also give this a WordNet synset, so a synonym set or a concept that's expressed by a particular word sense. So WordNet has these identifiers for each of their 117,000 word senses. And we've gone through all 117,000 WordNet word senses one at a time by hand in an enormous project years ago to map all of the lexicalized concepts, the word senses in WordNet, to SUMO. Similarly, the next word, kicks, has a lemma or root form of kick. It's a verb. It has a particular WordNet synset number, and it maps to the SUMO term of kicking. The is a determiner, and cart is mapped to the SUMO concept of wagon, and it's a noun, and then we have a period. And here we just highlight the word senses, the SUMO terms, and then the WordNet word, the words that correspond to that particular word sense. Here, WordNet's actually found that there are some somewhat famous people with the name of Robert as a last name, and it's identified them as well, and we don't really know which Robert's being talked about. Stanford Core NLP has something called BRAT, a visualization tool that gives you a graphical representation of its dependency parses, and we've augmented that here with the SUMO term mappings that apply. So Robert is the subject of the sentence, kicking is the verb, the is a determiner, the direct object is the wagon, and these little bits of extra information beyond just that it's a verb and it's a noun and that there's some dependency. The notion that one thing is a subject or an object or an indirect object in the case of intransitive verbs is very important semantically. And so that's really the main thing we get out of dependency parses beyond basic parsing, like something like the Brill parser or Google's Parsey McParseface. Those are just part of speech taggers essentially. But Stanford goes a bit farther and gives you the syntactic dependencies, and those start to get us a bit closer to the semantics we need. So as the output of the Stanford dependency parser, we get that there is a sentence, the root of the sentence, the root of the tree generally is the main verb. The subject of the verb kicking is Robert. The direct object of kicking is the cart. There's some punctuation, there's a determiner. And then we go to the next step of, and this is sort of a different way of walking through kind of what I've already shown you up top. There are different representations. These are just sort of more programming style representations instead of a graphical representation. It's not broken down in the same way. But here we see how we annotate the Stanford dependency parse triples with information about the SUMO concept that corresponds to each of the relevant or semantically relevant words in the sentence. We also add back in some information about whether nouns are singular or plural, because that, of course, is really important if you want to develop a logical expression. It talks about whether there's just one thing or several of the things. We need to maintain tense. So kicks is in the present tense, but we also have past and future. The cart is singular. There's just one cart. And we also keep these lemma forms. So not only that kicks is the original form, and that's a present tense verb, but also that has the root or lemma form kick. And then finally, and the most experimental portion here, is where we try to take these augmented dependency parses and turn them into an actual expression in first or sometimes higher order logic. And here we have a SUMO expression in the suo-kif logical language. We have an existential quantifier. There exist three things. One is a male human named Robert. The other is a kicking event. The agent of the kicking is Robert. The patient or object of the event is the cart. And there's a wagon, Robert's a human, etc. So we start, at least for basic sentences, to be able to get a full deep semantic parse. Now, there are lots of other systems that have produced things that look kind of like this, or at least like this first bit. They look like triples, but they use words as though they were logical expressions. In most systems that aren't backed by an ontology, kicks doesn't mean anything outside of the context of this particular sentence. All the semantics about kicks in these other more primitive systems is developed from the sentence itself. But of course, kicking has a lot of semantics associated with it. So if we just click on kicking, then we'll get the SUMO definition of kicking, which is, for example, here, that it is something that is done with the foot. The foot is the instrument of the kicking, and it's part of the animal that is the agent of the kicking. That's really essential information. A kick is not a punch, it's not a slap, it's not a push, and all of these things that you and I know about the world, that we know about kicking, somebody has to tell the machine so that it can make reasonable inferences. Right, so this is just a quick introduction to why I do all this work with semantics and what the semantics can be for amongst many other functions. And then in a later bit, I will sort of walk through a bit more of this. But I wanted to give you the punchline first, if you will, albeit a punchline that's very much engineering and science oriented.